Uh, yeah, so I was thinking just kind of could have a conversation about sort of intersections between your work and my work.
Yep.
I think that I've been thinking so much about distributed stress minimization. I
Mm,
think it's just an absolutely beautiful frame.
mm,
And sort of the various fields of the body, we can say. And
mhm.
then so I'm coming from the perspective of sort of this research into sort of formal research into consciousness, we can say, and then this frame of vasocomputation, this idea that tension in the vascular system essentially sort of holds Bayesian priors about the appropriate range of the neural system. So yeah, I guess to begin, like I'd love to hear distributed stress minimization from directly from you. What's going on there?
Yeah, yeah. So, as you know, we're interested in various cognitive mechanisms in really unconventional substrates. And I've been thinking a lot about most recently about how to measure stress in unconventional systems. And in particular, the use of for us the use of stress as a stress reduction as a driving variable for anatomical homeostasis. So the idea of cells and tissues having to adjust and both anatomically but also transcriptionally and physiologically to instantiate specific goal states that they have that then pull and so this process pulls them along. So our latest framework, and much of this is still unpublished, but what's coming out now is that we can use various stress markers to identify to basically show how these loops, in embryogenesis you sort of go stage by stage, right? And we can actually see the stress. So at the beginning there's a particular target morphology, and we study the one that's set by bioelectrics. There may be others, but we study the bioelectric one. And the target morphology doesn't match the current anatomy at all, and so the stress goes up and it works like hell to get there, and when it does, it goes down. But by then the bioelectric state has moved on again, so it happens again and again and again, and it keeps pulling it along through all the stages, and then eventually it sort of equalizes. And then we can talk about aging and things like that separately, but this is the kind of thing we study. And in particular, what I was what I wanted to also discuss, first of all, everything that you've seen in the vascular system I want to hear about, but also how do we measure it in really weird systems that are not biologicals at all? So what does stress look like in a gene regulatory network? What does it look like in a physiological circuit? What does it look like in other kinds of processes? Some sort of generic metric that we can apply across substrates.
Right. Yeah, fascinating. So I was thinking yesterday about how sort of there's this sort of distributed stress minimization that you talk about, and like if a cell isn't in the right place, then there will be stress, and like cells kind of emergently coordinate to sort of get the cell into the right place.
Yeah.
And kind of the bound of a system is the empathy of the cells in some sense. And I was thinking about how different systems may have sort of different currencies of stress.
Mm.
So first of all, and like how does that work? And sort of, what is stress in endothelial cells, and what is stress in neurons, and what is stress in glial cells, and so on, and how do they communicate? And I guess I had the loose hypothesis that um, there's sort of an intersystem sort of stress exchange, and it would be interesting to see if one of the kind of core levers the body has to sort of adjust, um, we can say mood or strategy or Bayesian priors or whatnot, is sort of adjusting the exchange rate of stress between systems. Like maybe in a rest and digest mode, stress in the stomach gets weighted 5x normal. So it's like stress gets distributed, but the stress that the stomach is holding sort of gets pushed into other tissues, where maybe in a fight or flight mode, like that's reversed or something like that. So just a side note there.
Mm-hmm. Mm-hmm.
Um, I can say that my notes here. I think that like you're you're touching on something that feels extremely important when you talk about sort of the cognitive glue and kind of things that kind of bind the system together, we can say. Um, and I would also say that like to sort of bring in vessel computation, one kind of core hypothesis that I'm sort of trying to poke at is that it feels like uh, it's kind of a very efficient compression to think of the vasculature as an agent. And we can say that the body is kind of this amalgamation of agents, all kind of emergently cooperating. And I guess like I think of the vasculature as it's like to what degree can you sort of ascribe different personalities to different agents of the body? I think is
Mhm.
a very interesting question.
Mhm.
Um, and so I guess so the sort of vessel computation baseline is that um, vascular tension stabilizes local neural patterns, or like whatever the sort of local substrate of compute is, we can say. That's the slightly more general frame. Um, Vascular tension basically freezes the patterns there. And so it's sort of a neat way to sort of hold certain things as constants where there's tension, and then other things can be left as variables where there's not tension. And vascular muscle, of course, is a form of smooth muscle, and smooth muscle has this latch bridge mechanism where it can basically glue itself shut, like the actin and the myosin basically stop sliding and get chemically glued. Uh, so then this can persist, and like I guess from my expectation is that these sort of latches, when vascular muscle sort of engages this latch bridge mechanism, and these maybe it's sort of actively defended or actively refreshed, or there's some sort of like metadata from the body, like we need that, then I expect that this can last for anywhere between minutes to hours to potentially decades. So kind of a very long-term prior. Um, and then of course it's like vascular tension is sort of um, gatekeeping the body's central currency, blood flow. And so if neurons don't get blood flow, they just don't have the like resources to adapt, to rewire, etc. Um, and so I've been thinking about that as sort of um, kind of a backup or kind of a almost like an RLHF system for the neurons
Yeah.
that if if some like big prediction error happens or whatnot, uh, the vasculature can kind of leap in and say, okay, like that didn't work. We're not going to let that happen again. If you get bitten by a dog or something, and it can kind of latch patterns into kind of a known safe mode, or um, maybe bring in this active inference frame like tension as a prediction. So you can say you latch a prediction that you will be safe in a certain situation. But of course, that reduces overall system dynamism. You basically block out certain parts of your dynamic range, which has downsides. So I guess like the story that I'd want to tell is that we're sort of this amalgamation of systems, and these systems are sort of amalgamations of smart parts, as you've described. And then what I want to say is the vascular system, or like people think of intelligence as sort of embedded in the neural system, and I think your critiques have been absolutely spot on. That and like even neuroscience shouldn't be about neurons only. Um, so I want to say that maybe, but like neurons are sort of specialized for long range communication. Um, and I guess I would propose sort of looking at smooth muscle cells in like with fresh eyes. Like what are these cells? What are they doing? And sort of what is their functional role? And like, I guess I see them as sort of uh, playing neurotic protector to the neural system. That if the neural system sort of can't handle something, the vasomuscular system sort of jumps in and tries to make it excuse me, make it manageable.
Mm-hmm. Mm-hmm.
So I want to pause there, and does that make sense?
Yeah, yeah, absolutely. Absolutely fascinating stuff. Really important, I think. Do you think so? So I was thinking about something a little related recently in terms of gene expression, right? So you have, I don't know, 20,000 different genes or whatever, and you don't have the metabolic resources to transcribe them all. And so one way to think about it is that the cell is making decisions about what to transcribe, fine. But another way to think about it is that could the genes actually be in competition for the attention of the transcription machinery, right?
Right.
So if there is this obvious overseer that is going to decide who actually gets transcribed, you would think that there would be some forces to start to hack it, right? Where the genes are trying to get the attention of the system. So my question in your case is, do you think that neurons, in addition to doing whatever it is that they're doing, are actually trying to get get the goodies from the vascular system? Is that a thing? Are they trying to hack the vascular cells at all?
Yeah, I mean, they'd have to be, right? And I think that, I mean, the sort of powerful thing here is like the vascular system is sort of holding the purse strings.
Yeah,
Uh,
yeah,
that like if the neurons don't get blood, there's just a hard cap on sort of
yeah,
what they can do, and I expect
yeah,
that they can. I expect that if we poke into neuron physiology, we'll find that there'll be like uh, I'm not sure if it'll be continuous or discrete, but they'll sort of drop into safe mode in a very clean, elegant way. Like they're sort of designed to sort of go through metabolic winter, we can say. Um, that there was this sequence of papers sort of starting with the hemoneural hypothesis by Moore and Cow,
mm,
and then moving into I think cognition is entangled with metabolism, Jacob et al.
mm,
And talking about how like a couple of kind of crazy unexpected findings. One being that blood flow in healthy tissue can vary by over a factor of 20. So not 10%, but 20x plus. And so we should expect sort of cells to behave, like have different sort of modes of operation depending on that. And then the second finding was that actually changes in blood flow precede changes in neural activity. That it's not that neurons, fire and use a bunch of fuel. It's that the blood changes, or like the blood comes, and then neurons change. Um, yeah,
so that sounds like it would be really interesting. And maybe it's already been done, but it would be really interesting to do some kind of a multi-scale neural network model where the cells are where the neurons are agents that also, there's some pressure to compute whatever it is, but there's also, right, if you want to do the computation that you're supposed to do, you also have to navigate your local environment and get the purse strings, so to speak, to feed you, right?
yeah, yeah. Interesting. And I guess I'm sort of pushing on that. I do think that like a very interesting sort of near proxy for attention, maybe blood flow, sort of turning up, Morgenkow described it as sort of turning up the sensitivity or the gain on networks. And it'd be interesting to see, okay, like how do neurons sort of compete for blood flow, and how do the algorithms of the body sort of punish defectors on that? Um, yeah, fascinating.
Mm-hmm.
Um, I think, yeah, I guess like the like corporation defection dynamics get pretty deep pretty quickly.
Mm-hmm. Mm-hmm. Mm-hmm.
Yeah. Um,
Are there By the way, something else you said about the different personalities, of the body and everything. I
Yeah.
just an hour ago, I had a conversation with Frank Putnam and Alexei Tolchinsky, and they were talking
Okay.
about, right, this business of dissociative disorders and the different personalities that can live within one body, and how they navigate their relationships. And one of the most interesting things that he said was that they have shifted clinically from, instead of trying to integrate, what they now do is provide. They literally have they make a bulletin board where the different personalities can leave each other messages. And so
Wow.
this is actually it's you achieve this. It's a stigmergic medium where you get to like leave these messages for each other and communicate that way. But as a result, the collective becomes more functional and integrated towards goals, but it's not the thing where you hope the pieces disappear in favor of the whole, right?
Right.
So I wonder, do you see in these vascular networks, do you see how many agents do you see? Do you see multiple agents at the same level? I mean, of course, there's multiple levels, but at the same level, are there regions? Is the whole thing kind of tightly integrated? Has
Yeah.
anybody done things like any kind of causal emergence metrics on the data, that kind of stuff?
Right. I haven't seen that. That'd be fascinating. My expectation is that a lot of this logic is local, that
Mm-hmm.
and maybe may sort of have sort of local organs as kind of the big attractor, or like kind of the semi-sovereign domain, I guess I would say, and then sort of the tissue trying to serve that domain. So the stomach being a domain and the heart being a domain, brain being a domain, and so on. So yeah, it'd be fascinating to dig into that. But the sort of mechanisms of like how the muscle cells are organized are like the vasculature is not one big muscle. It's like a bunch of tiny muscles.
Mm-hmm.
So yeah, and I guess like part of this thesis is that um, a lot of the challenges of being a human living in modernity is that sometimes these vascular clenches and latches, these sort of crystallized priors, they're too sticky. That a, like an absolute central challenge for humans is how do we release this tension? It's like not all of it gets properly garbage collected, we can say.
Mm-hmm.
Like, and we can say, okay, I got to pick up my daughter from school. I'm going to remember that, and like that's sort of instantiated with a prediction slash like a tension in a certain part of my nervous system. And the vasculature reaches everywhere. Anywhere there's blood flow there, anywhere there's neurons, there's blood flow, and anywhere there's blood flow, there's this muscle. Um, but I suspect that as we go through our day, making predictions, making active inference predictions, we sort of naturally like clench and release, and it's kind of seamless. But sometimes sort of cruft builds up that if we look at this as kind of a form of side channel memory, that of the proper dynamic range, or like don't use a big part of the range, or like remember this pattern, freeze this pattern, or whatnot, then over time you'll just naturally get situations where uh, the resources aren't released to the system. They're just you maybe you were interrupted in doing a task, and like your body was sort of holding something, and it never got the like task completed trigger such that it could release. So my expectation is that this is a pretty clean description of, first of all, what we can call trauma, this sort of, shards of information sort of held by tension in your nervous system. And like I have a friend, Warren Winter, who described explained what a Wilson affordance was. Like as we perceive something, we don't see it as it is. We see uh, the object in terms of what I can do to the object and what that object can do to me. So if if you see a dog, maybe you see, oh, like I could pet that dog, but also, oh, that dog could bite me. And of course, if something bad happens, then kind of the negative sort of Wilson affordance might get latched into the system. But yeah, I guess like I see it as kind of a neat explanation of trauma, which would be pretty exciting if, this is kind of the home system where that lives. But also just in terms of, I've been kind of uh, trying to dig into the Buddhist frame for a while, and it feels like what is talked about in terms of sort of, there's sort of this self, this sort of immutable, set of constants that sort of prevent um, maybe a wider aperture on reality, we could say. That this might be a particularly good fit for explaining that as well. And that it's not that, if we had a magic wand and we could open all your vascular tension, like good things would automatically happen. Like probably some of it is very load bearing. But I do expect that, if we sort of like if we were to track the sort of fine vascular tension of meditators as they kind of go through the path, we'd see some sort of opening where maybe some networks that were sort of latched when you were two, when you were three, etc., um, may reopen, and sort of you get this much wider like sense of possibility. So those are the like two applications that I would be very excited about.
Yeah, yeah, yeah. Um, Eric Hole in our center has been developing some more recent new metrics for things like
Yeah,
uncovering new levels of causality and so on. I wonder, is are there presumably there are lots of data that this could be applied to, yeah, to see what is actually going on in that system as far as integration and so on.
yeah. I've been a huge fan of Eric. I think his yeah, EC 2.0 looks really
Yeah,
good. So yeah,
yeah,
I'll have to think about that.
hmm,
Um, nice.
yeah. And
Yeah.
another interesting thing to look at maybe, and I don't know how hard or easy it is to do these in humans, but and also there's not that many of these patients, but there are some really interesting exceptional human cases where people have very diminished brain volume and yet normal cognition. And I would be interested to know what's going on right in the vasculature and the muscle in those in that case, is it like taking over some of the processing? Does it matter?
Right. Right. Yeah. Fascinating. Well, I mean, one question that seems like it's at the intersection of what I'm looking at and your work, is this idea of distributed stress minimization between types of contractile tissue in the body and also neurons.
Mm-hmm, mm-hmm,
Um, so, I mean, I do have the expectation, first of all, that like this system is trying to minimize net expected stress. I mean, if you see a tiger and like your stomach clenches up and it's like it is a high stress state, but it's lower stress than being eaten. And so I think like it's kind of trying to multiplex stress across, uh, you know, we can say Bayesian features or whatever, and trying to sort of um, minimize total stress. But I guess oh, I lost my train of thought. Sorry about that. Um,
yeah. I mean, Richard Watson and Chris Buckley and those folks have done some models. I don't know how much of it is published, but they've done some models on the computation in networks of springs and this kind of like the physical stress kind of dynamics and how they allow the network to compute. So I think that's very interesting, and I think this intersection of stress as it's understood in cognitive science, stress as it's understood in biology and physics, and also in things like in mathematics, right? So geometric frustration and so on.
Right.
I think it would be very, very interesting and helpful to actually connect all of those, because I guess the null hypothesis is that those are all different things and we just call it stress. But my suspicion is that it actually is all under. I mean, I think geometric frustration is real frustration. So on the very end of the cognitive spectrum, like I think it's actually right. That's alignment. Misalignment of your parts is probably a fundamental aspect of stress and frustration in composite cognitive systems.
Yeah, absolutely. And so I remembered what I was going to say, but just a quick note. So in 2016, I wrote just a short book, Principia Qualia, that laid out what I call the symmetry theory of valence.
Mm.
And this idea that if we have kind of a formalism for an experience, and I mean, this is a hard thing to construct, but if we sort of had a perfect mathematical representation of what it feels like to be you or what it feels like to be me, then the symmetry of this mathematical representation would sort of correspond to, like exactly correspond to the pleasantness of the experience. So basically, it's kind of a formal mathematical way of saying harmony in the mind is the thing that feels good. And so, yeah, what you say about geometric frustration definitely rings a lot of bells.
So what do you think about systems, simple systems in which everything is aligned and harmonious? So, a magnet or something where everything is nicely aligned. What's
Yeah.
the is that for that minimal system, is that can we say that it's somehow maximally that it has valence at that point?
Right. Well, I would say that there's going to be a couple requirements. So one being the system has to be conscious. So this, like the symmetry theory of valence, is not a theory of consciousness. It's a theory of valence. So if we can point to a conscious system, then sort of and then kind of construct a formalism for what it feels like to be that system. Then I do think that symmetry and formalism corresponds. Like there's like an identity relation with valence. But yeah, just kind of a simple magnet may not sort of may or may not lead to consciousness. I would also say that so I mean Eric studied with Tononi, and like one of Tononi's frames is that you need integrated information for consciousness. And sort of, I do expect that there to be an interesting trade-off between sort of enough complexity such that you have some integrated information, and then enough simplicity such that everything is like nice and symmetrical and harmonious. So yeah, that's maybe worth noting.
Yeah.
Back in on the sort of distributed stress minimization frame, I'm reminded of sort of the different types of muscles, and I'm a big fan of like Joe Bullock's work on sort of maybe like muscles are a little bit different than we think they are, and so on. And like I do suspect that there's going to be this interesting sort of we could say leakage of stress from one muscle type to another muscle type. And Uh, so like if you have like a lot of skeletal muscle stress, maybe some of your smooth muscle also sort of picks up some of that tension and so on. And that this may be like computationally interesting in a lot of ways, especially insofar as um, contractile tissue that's not sort of finely regulating the neural system bleeds into this vascular muscle that I think is finely regulating the neural system. Um, and there's also like fascia, which like it's kind of a wild card topic. A lot of people ascribe very interesting properties to fascia. I think it's very interesting that it's so electrically active. It's very conductive. Um, and I guess one thing that I've been sort of wondering, and I'm really curious what your instincts say. Uh, so fascia can't exactly latch, but it can sort of durably contract. It's much sort of slower than VSMCs. VSMCs, can operate on the scale of hundreds of milliseconds, whereas fascia maybe a minute or so to contract. But once contracted, they can sort of rewire, and that's the new default.
Hmm.
And I guess I'm wondering. Um, I suspect that VSMCs might have this fine regulatory effect on neurons, but what do you think fascia regulate? And what do you think contractions in fascia might sort of quote unquote latch?
Yeah, boy, that's an interesting question. I don't know. Yeah, I don't know. It's really, I think, one area that might be relevant to this is acupuncture. So I've seen some good. Helene Langevin in Vermont has these really interesting experiments. She's got this full thickness skin tissue model where she puts the needle in, and you get this lateral view of all the layers and the fibroblasts and everything, and you put the needle in and you sort of twiddle it. And what she shows is that the fibroblasts grab onto the needle, and then by twisting it, you're pulling you're basically making these tensile forces that spread very long range. So I'm not an expert on any of that connective tissue, but it's almost certainly there's going to be some kind of mechanical computation there, right? I don't know what the endpoint is, but there's got to be.
Right.
I would assume nature is using it. I mean, that one thing that Josh Bongard and I have been developing recently is this idea of polycomputation, where the body is a collection of observers that is interpreting each other and all the physical events in every which way, right? So I would be shocked if a dynamic like that had no observers paying attention to it.
Right. Fascinating.
Yeah, but I
Yeah.
don't know what exactly. I mean, I don't know which processes exactly would are tuned into it, but I'm sure something's watching it.
Yeah. Yeah.
Yeah.
Nice. That's great. So one thing that comes to mind also, I think you're one of the experts, if not the expert on sort of the electric fields of the body. Um, and I appreciated your somewhat recent tweet about how like it's really hard to measure fields, and like it's often you can measure VVAM, like the membrane potential and so on, but so caveats about it's sort of hard epistemologically to approach this topic, but I'm really wondering sort of uh, what's sort of the basic electrical layout of the body. So as I understand it, you have cells have a strong membrane where there's I guess like the charge density of the membrane is equivalent to like a lightning. So it's like very small but very potent for its size. And then mitochondria have even stronger cell membranes or mitochondrial membranes. And then you also have things like fascia, which conduct electricity. Um, I understand that bone is essentially calcified fascia, so that's also very electrically conductive.
Interesting.
Um, you have things like wound healing seems to, or like wounds generate a stronger electrical field, such that maybe that helps things kind of reorganize and heal. Um, but I guess I'm wondering, um, like from the perspective of consciousness research, uh, where I am sort of like electromagnetism is a sort of particularly interesting sort of way to sort of describe um, the organism and like whether or not consciousness sort of lives in the EM field, that's a rabbit hole. But uh, I'm looking at this in terms of uh, Wolfram's branchial space, where sort of an object's true shape lives in this branching space of sort of possible ways to decohere. And so if like I guess I have the idea that a mind is kind of a shape in branchial space.
Mm-hmm. Mm-hmm.
Um, and I'm very curious what the body's shape in branchial space could be.
Yeah.
And I guess it's my expectation that the EM fields of the body would say a lot about what our sort of true shape is, our shape in branchial space. So, I don't exactly know the questions to ask you, but
Yeah.
that's kind of the setup.
Yeah. So I haven't yet figured out the relationship between my model and Wolfram's model of that space. Um, I think that what I currently think is similarly that there is a basically what used to be called a Platonic space of forms, right? And that what we are building when we make cells, embryos, biobots, AIs, whatever, is we're
Yeah.
making interfaces. Yeah, we're making interfaces to specific patterns in that space. And I think in particular, um, it looks like the bioelectric circuits are very sort of versatile in that way, and they can pull down lots of different patterns. So in the body, you have a huge number of these things. So you have static forces among the molecules. So you have different distributions of static charges. And then you have voltage gradients across intracellular membranes. So Golgi, ER, nuclear envelope, of course, mitochondria, all of those things have a voltage gradient. Then the cell itself has a voltage gradient across the membrane. But even that isn't one gradient. A typical cell has many different voltage domains across its surface. It's like a soccer ball of different domains. And then the cells come together into tissues and epithelia. We will have a transepithelial potential across them on top of that. Um, then some people, I mean, Becker and other people measured this weird longitudinal electrical potential, which is, so basically body scale voltage differences, right? Kind of very long range. Um, and those are all the static electric things. And then on top of that, you've got the electromagnetic components, which some of the voltages change very slowly. So the induced magnetic field is very low, but there are other events that produce natural EMFs coming off of living tissue and going into the ultra weak photon range, right? So UV photons. So it's sort of like just an enormous amount of these kinds of things going on at different scales, at different frequencies, all the way from DC, which is what we study, to light, basically, and all of those are kind of interpenetrating at the same time, and the cells and the other systems are trying to make sense of all of it. They're kind of
Wow.
swimming in this soup of signals.
Yeah. Fascinating. And yeah, I guess like I'm cognizant that I'm uh, sitting with the expert here, and like what to you has been the most surprising in kind of studying this system?
Interesting question. Well, I guess the most surprising thing to me so far has been, first of all, just how plastic it all is,
Yeah.
and the idea that evolution apparently has really spent most of its effort on creating a system that is able to creatively interpret the memories that it has, whether those are genetic memories or behavioral memories. I've been playing with this bow tie architecture thing where basically at any given moment you don't have access to the past, you have, but you're aimed forward in prediction, and you have to take the prompts that you've been given, whether those are your genes or your engrams from previous experiences or whatever they are, and you have to
Yeah.
construct the story, right? And so just the ability of every day we see these amazing things that have no evolutionary precedent as such, but what you're seeing is the evidence that basically living things are these amazing sense making systems at multiple scales, and they're using all of these computational affordances, all the different layers of the body to tell coherent stories that may or may not bear any relationship to the previous story they were given.
Right. Fascinating. Wow. This kind of reminds me of sort of looking at the vasomuscular system and sort of this idea that maybe in sort of some idealized setup, the nervous system is kind of this. I think of it like a set of wind chimes, and like as sensations kind of come in and hit it, then sort of by the presence or absence of certain sort of hums, you can build a model of your environment.
Mm-hmm.
And then you have these sort of latches, these sort of tiny areas of chronic tension, and like the resolution on these, it's like between 100 to 400 micrometers. So that would say just in the brain, you could have somewhere between 21 million to 1.3 billion. I'm calling them vascular addressable units
Yeah.
of differential tension. And so like these can kind of save patterns. And over time, we sort of accumulate these sort of little points of tension, which sort of become a predictive story. They sort of not only encode what we expect from our environment descriptively, but what we expect from our environment prescriptively. They're sort of very sort of active inferency, like I will make my environment into this, not just I'll like expect this to happen. And so like over time, it does seem like we sort of begin to live in this story.
Yeah.
And sometimes, like, I guess part of the Buddhist critique is that actually this is bad in some ways, and that it's actually hard to not live in the story.
Yeah.
And this, I think it's interesting hearing you say this, that you have all these systems sort of doing something that feels very similar, and that there are stories upon stories in
Yeah.
a lot of systems.
And this is right, and this relates to I'm working on something I jokingly have provisionally titled femto Buddhism, where
Amazing.
you sort of ask the question, and I've had this discussion with the Buddhist scholars, and I'll say, well, so all living beings, right, under delusion and must be liberated and all that, yes. So cells, right? Okay, yeah, I guess so. So molecular networks inside of cells, like what does it mean, right? Chemistry presumably doesn't make mistakes. Developmental biology definitely makes mistakes. And so is there a point in which you say, and I mean, I think people's typical intuitions is that no, that stuff doesn't accrue karma, it doesn't get liberated, it just kind of does what it does. But then you have this amazing living stuff, and it has these issues of, right. But actually, can you actually take this all the way down, right? So I'm interested in taking some of these concepts of what it means to be in delusion about your environment, and what does it mean to be in a flow state, and and have sort of more or less direct access to this to this information, as opposed to sort of painstakingly and mistakenly often trying to work it out, and how does that relate to kind of least action laws? When you have a photon that doesn't have to worry about calculating all the different paths, it just kind of always goes in the least action path, and what's happening, right? So from there we sort of dip into this, as from the particles, we dip into this place where we as living beings have to work really hard to, we fight for information and for trying to figure out what to do. And then, some of us, some of the geniuses or the exceptional people, then they get into the flow state and they're like the photon again. So
Right.
what does that curve look like? I think there's a lot to be said about what chemistry is doing from that, from that perspective. And the other thing that I think now I'm thinking, having talked to you about this, I think we have something coming out with where we took xenobots, which are these like novel frog-based constructs. We introduced a nervous system, and we wanted to see what does a nervous system look like in a being that has never had evolution shape the structure of its nervous system.
Right.
But we don't have a vasculature there. And so now I'm thinking maybe the next thing we got to do is we got to introduce some vasculature and
Yeah.
see what that looks like.
Amazing.
Yeah. There's something else I wanted to show you before we break.
Yeah, please.
You want to see a really weird vascular hydraulic computer? So
Absolutely.
I don't know if you've ever seen this. This is something Narosha Murugan worked in my lab on this. This is Physarum, the slime mold. And Physarum, like it does mazes and things like that. But I want to show you one particular thing that you might appreciate. So here's a branch of the slime mold. Here's another branch. This thing has been injected with these little they're fluorescent beads, basically. Okay, and so we're just going to track the fluorescent beads, right?
Right.
And so what you can see here is right now it's just acting like a Y splitter in a hose, right?
Uh-huh.
But each one of these little things is independently addressable, because you can see
Uh-huh.
that it like shut this off. This thing's still going crazy. This one's completely shut off. So this amazing fractal thing that has just tons and tons of these branch points, if all of them are independently addressable, first of all, what network is controlling which things get turned on and off, right? And you can even see like sometimes it goes backwards, and so I don't know if there's directionality to the actual synapses here, but they're synapses basically, because you can easily imagine a mechanism where based on prior experience this thing gets turned on or off, right?
Right.
So
That's beautiful.
I thought that was kind of cool, and like what the heck are they computing, first of all, and what, again, there should be these kind of at least two overlapping systems where there's the hydraulic system, but on top of that something has to be guiding the opening of the branch points and the kind of the decision making there.
Yeah, absolutely. Super relevant. And I mean, it does also kind of call into question, like, how do you figure out the causality between the systems? I
Yeah.
mean, everything is regulating everything else, but can we sort of say, this is the dog and that's the tail, or like, and whether it's grandeur causality or there are different metrics, and I think Eric's work would be relevant.
Yeah, for sure. For
Honestly.
sure. Yeah, super interesting.
Yeah.
Yeah, amazing. Thank you so much. I love your work. I think it really opens a whole new avenue of all this stuff. And I think, I think we really need to start just looking more carefully at the vasculature and the muscle, but also this kind of broadens and helps us to try to define metrics of stress that in systems that are not directly mappable onto each other.
Yeah. Oh, likewise. I mean, I'm such a Michael Levin fan. Just what you're doing is just amazing. So yeah, thanks.
Yeah, thanks so much. I think at some point it would be cool. I'd love to. We're all full for this semester, but maybe in the fall, if you could give a talk to our center, I think that would be really awesome.
That'd be amazing.
I think people would love it. I think they need to know about this stuff. So yeah, thank you. Let's keep chatting. If you have any thoughts on kind of general definitions of stress in diverse models in general, I would love to talk some more about it.
Yeah, absolutely. And just to inject one more kind of observation that
Please.
I think that like this idea of boundary conditions in physics, in biology, it's sort of very important. And I think that you have kind of this very fresh perspective on sort of what defines the boundary and sort of or what defines the boundary of cooperation or morphological boundary and so on. And I guess like one of the big core challenges in consciousness research is determining the boundary of a conscious system.
Yes.
and
Yes.
and that I think that your work definitely seems relevant. And I would also say that, from my bias perspective, that this sort of branchial space view, this sort
Mm.
of viewing objects as sort of um, shapes in branchial space,
Yeah.
uh, like the true shape lives in branchial space perspective. That I do expect that um, understanding like uh, uh, your work in terms of like what determines boundaries in organisms, biological systems, and then sort of does that lead to sort of a natural boundary condition in branchial space? This seems very like I don't know how to solve that, but maybe you do.
Yeah, very interesting. Okay, well, it sounds like yeah. We should we'll have another conversation about the boundary, the whole boundary thing. I think it's super important.